Today we're doing a single diagonal truss approximation example, and as you can see, this truss is indeterminate. So if you try to solve it using statics, you'll find that you don't have enough equations to actually solve the problem. So instead, we're going to approximate some forces until it becomes determinate, and then we can solve it with method of sections and method of joints. So the approach to this problem is to replace the truss with an equivalent simply supported beam right here with the exact same loading as the truss. So like we're going to put these 20 kilonewton forces each at 3 meters, just like it is on the indeterminate truss. Then we're going to solve for the reaction forces in the beam and create the shear force and bending moment diagrams for that beam. We're going to use the bending moment diagrams and this equation right here in the bottom right to find the top and bottom chord forces. This basically just says, okay, so one of the chords is in compression and one's in tension, and to find the magnitudes of each chord, we're going to use the bending moment at that location and the truss height. Next, we're going to use the shear force diagram to get the diagonal forces using the single diagonal assumption. Basically, the assumption is that we used to have something that looked like this in the panels, one brace in compression and one brace in tension, but all of the compression braces have buckled. Therefore, we're left with a bunch of single diagonals. Also, I should note that we're really only concerned with the y component in these diagonals, and we're going to use the shear force diagram to determine the magnitude of that y component. So enough explaining, let's just solve the problem. And I've also put the equations in the top right-hand corner here so you guys don't forget. So the first step to these problems is to draw the equivalent beam. So I've drawn a simply supported beam here and then labeled it exactly like the truss. And I'm going to put the loadings 20 kilonewtons every 3 meters. Okay, so since everything is symmetrical, RA is going to take half of the loading and then RB is going to take the other half. RA is equal to RB, which is equal to 20 times 5, which is all those point forces, divided by 2. So basically, one side takes half, and then the other side takes the other half. All right, guys, so now that we have the reaction forces and we've set up the equivalent beam, we can find the shear force and bending moment diagram for this beam. So we start at RA, which is 50 kilonewtons, and then we drop 20 each time until we finally reach the other side where we go back up to 0. All right, so now let's move on to the bending moment diagram. Now the increase in the bending moment diagram can be calculated using the area under the shear force diagram. So the first one is 50 times 3 meters. So we're going to get 150 kilonewtons times meters as the first increase. And then plus 30 times 3. So that's plus 90 meters. And we're going to go up to 240 kilonewtons times meters. And then we're going to peak at 270 kilonewtons times meters at midspan. So let's start with the chord forces. I'm just going to do step 2 right here. And we're going to use C is equal to T, which is compression is equal to tension. So the magnitude is going to be the same, which is equal to the moment at that location divided by the height of the truss. So I've circled the most critical chords on the truss, the ones at midspan. That's chord IJ and chord CD. So what we're going to do is find the magnitude of each of these chords using the moment at that location. So what moment do we use? Now, the hint was it's in the most critical location, but all we have to do is really just draw an arrow here to figure out which segment on our bending moment diagram is responsible for that panel on the truss. And that's the panel between 6 and 9 meters, right? So we're going to use 270 kilonewtons times meters to find this axial force. All right, so C is equal to T, which is equal to 270 kilonewtons times meters divided by the truss height, which is 4 meters. 67.5 kilonewtons of axial force for the top and bottom chord in that location. So step 3 is to find the axial force in the diagonal. Now we've made the single diagonal assumption. So we determined that, okay, pretend this is a panel. There's only one bracing and it's in tension. And we have some shear force acting vertically like this. Therefore, the y component of that bracing is equal to the shear force. So first things first, we're going to draw our little special triangle here. We have the truss panel width of 3 meters, and then the height is 4 meters. That means that this diagonal length is 5 meters. And the y component here is 4 over 5. This is force HC right here. It's diagonal HC. It's circled right here. So we're going to say, okay, 4/5 FHC, so the y component of FHC is equal to the shear force. Right. So what is the shear force at that location? So this is between 3 and 6 meters, and that is right here on our shear force diagram. Therefore, the shear force at that location is 30 kilonewtons. So 4/5 FHC, which is the y component of that diagonal, is equal to 30 kilonewtons. Then solving for FHC, we get an approximate value of 37.5 kilonewtons of tension in the diagonal at that location. And that's basically it. You just keep going from there until it's solvable using method of joints or method of sections. And by the way, a lot of these questions are symmetrical, right? You get a symmetrical truss. So the magnitude in this guy is going to be the same as in this guy, right? And then the magnitude of the chord forces here are going to be the same on the other side. They both use the exact same bending moment, right? So it's actually very simple to make it determinate, and then you're going to use method of joints, method of sections, starting at, one of the supports, and go from there and solve it. Anyway, I hope that helped. I hope it wasn't too long. I really appreciate you watching this video. Like and subscribe, and hopefully the next video on the double diagonal helps you as well.